Hello. So welcome to the talk about running Wasm in React Native apps. And for some of you at least, I see the confusion, the despair. Couldn't you already do this? Like, doesn't WebAssembly run everywhere already? Can't you already run it in React Native apps? And the answer is, well, sort of. The prior art, some of the existing solutions, they rely heavily on serialization of data and use an old architecture of React Native and are very limited in the Wasm features. And the good news is that this gap is closing. And today in this talk, we'll share the recent advancements in bringing WebAssembly to React Native. Ultimately, we're here today to talk because we share a goal around bringing WebAssembly to React Native, and also extend an invitation from your community or to your community to join in and be a part of the React Native community and ecosystem if you want to. Okay. First, a bit about myself. My name is Kræn Hansen. I work as a senior software engineer at MongoDB. I help build developer tools, primarily Compass. It's an Electron-based GUI application to query your database and administer your database cluster. I also help maintain a TypeScript SDK for the thing that's formerly known as Realm.js. It's a database. It's a lot of TypeScript and some C++, and it supports multiple runtime environments, operating systems, and JavaScript engines. Outside of work, I'm a proud father of 3 girls, 2 6-year-olds and a 2-year-old toddler. And I live in Roskilde, just west of Copenhagen in Denmark. Besides spending my time with my family and at work at MongoDB, I also like to build in public. And for this work, I accept sponsorships on GitHub, and in particular from Callstack, which is where Robert works. So you can write to me on Blue Sky, and I would appreciate any feedback that you have for the presentation or whatever I do.
My name is Robert Pasiński. I'm a senior software developer at Callstack. I'm based in Szczecin, Poland, which is the northwest part of the Poland. I'm a programming enthusiast. I do anything programming related. I actually started my journey as a web developer, moved towards development of mobile apps and native apps. I was always interested in low-level juicy internals, so compilers and anything related to this topic. I'm working at an incubator team at Callstack. This is our new team that's focusing on improving developer experience and creating innovative solutions. You can find me on X or Twitter, however you call it, and on Blue Sky. And yeah, this presentation will be about our journey with WebAssembly in React Native, which is one of our efforts at incubator team at Callstack.
Awesome. So React Native. I imagine most of the folks in the audience is familiar with WebAssembly and less familiar with React Native. So just a quick rundown. In its essence, React Native is this toolkit to build cross-platform native apps written mainly in JavaScript and TypeScript. And they run on iOS, Android, desktop, macOS, Windows, and also on the web. It's very popular. It's widely adopted, more than 3 million weekly downloads on NPM. And it has a very large ecosystem of more than 1,000 actively maintained packages targeting specifically React Native. It is stewarded as an open source project by Meta and initially released 10 years ago as of yesterday. So it's pretty old as well, or it's been around. So one part of React Native is React. It's built around this most popular framework for building reactive UIs. And it enables this delightful user experience with a lot of the native look and feel. And that's because the other part of React Native is native. And it has these application UIs that are composed of the actual native views provided by the platform underneath. So it's not a web view rendering some website. It's actually native buttons, native view components provided by the platform. And in the context of this talk, there's also a few things that I want to highlight. The default JavaScript engine for these React Native apps, it used to be React Native Core, and it used asynchronous message passing between JavaScript and the native code. That's how it used to be. That's the old architecture of React Native. And the new architecture, and nowadays, we use another JavaScript engine called Hermes, and it's built by Meta specifically for React Native, and it focuses on basically optimizing the first time to interactive for your apps. And that also means that it brings almost no runtime APIs. It's a very narrow JS engine, and in particular, it doesn't bring WebAssembly.
Yeah. So the question is, why bother with WebAssembly in React Native? To answer this question on why we are thinking about this is to reach our goal of truly universal applications that work on both web and native with the single code base. We at Callstack really love React, and we have this very ambitious goal which we refer to as React Universe, where we want to use React for the UIs everywhere we can to truly create the universal applications. And how can we achieve this? So we have React Native, which we create our native applications with. And we want to embrace WebAssembly growing ecosystem. Let's stop on that and focus on the environment and the current status. So the cool part about JavaScript, and also the worst part, is that there are multiple runtime environments right now, which is also a good thing. But it can be hard for package maintainer to support all of the runtimes. And it gets even more complicated when you have like this narrow runtime, like React Native. So those packages are only running on React Native due to the limitations. So you have like Node.js, which is the first player of this kind and the biggest one. And we have like two younger and cooler kids on the block, like Bun, which is written in Zig, and Dino, which is written in Rust. And there's also the browser, which is the biggest environment, and it's also very specific. So this makes a bit of a challenge to use a single registry for everything that has a JavaScript in it, but cannot run in different runtimes with ease. One of the issues is that the packages can depend on web APIs, which makes them browser-only unless you use the web API shim. You can have packages that, for example, use Node APIs to bring native functionality to Node, but then those packages are not available on the browser, right? So this can cause some issues when looking for third-party dependencies, and this also affects React Native right now. So let's talk about what's the current status of bringing native functionality to React Native. So how it is done today? You can extend React Native with native functionalities using what's called TurboModules. These are written in C++ mainly, and you can use Java, Kotlin for Android, and Objective-C and Swift for iOS. The later ones are used mostly for interactions with UIs, because you can write your headless code in C++, but when you want to interact with native controls and widgets, you're limited to the native APIs, because as Kræn mentioned, React Native uses native components. It's not like Flutter, where it's emulated. It's truly native. So we need to use those languages to cooperate the UIs. Yes, and you can access the JavaScript environment through what's called JSI. As Kræn mentioned, there was first JavaScript core, and we migrated to Hermes. And both of those engines are abstracted away using JSI. So it's a very generic interface for communicating with JavaScript. And it's using C++ for the communication. To bring something to React Native, we start by writing the API contract in TypeScript, which we call the spec. Rather than writing it by hand, we are using a tool called CodeGen that, looking at this TypeScript spec, it generates the corresponding native code to allow us to implement and bring this functionality to React Native. Bringing the bridging between TypeScript and native code is also generated, so we are not limited to primitive types. We can also communicate using complex types like records, classes, and such. And this code is also automatically generated. As you can see, if I'm an app developer using TypeScript, that's a lot to grasp. That's a lot of languages I need to learn and use to bring something to React Native. This is an example of such TypeScript specification. As you can see, it uses standard TypeScript semantics. It's a simple example of from the documentation, I think, that specifies a simple storage interface, like local storage or session storage. Yeah, it acts like a contract. So this is where the communication between JavaScript world and native world is implemented. The good part about this is that this contract is completely type safe, and we can write it in TypeScript, or if you are like for Meta, they prefer using Flow. The generated code looks more or less like this. This is just a snippet. There's more code below, which is not important to us right now. What is important is that we are provided with an abstract class, which we need to implement and derive from. And as you can see, it uses the native types. So we are not working with JavaScript bridge types. We get access to native string or optional. So yep, the integration with the native C++ libraries is easier this way. One of the biggest shortcomings is that this approach does not cover the web. It's mostly focused on native applications, native mobile applications. And you write TurboModules for React Native, and when you want to bring your application to web, you're out of luck. Also, when you want to integrate external libraries, such as SQLite, for example, or any crypto library, as a JavaScript developer, I need to bring this library, integrate its build system, and expose the API. So for Android, you need to integrate with Gradle and CMake. And for iOS, currently it's CocoaPods, but we plan to migrate to Swift Package Manager. This approach is not so straightforward when trying to integrate, for example, a Rust library, because there's cargo, and integrating it with different build systems, different platforms, the triplets, it can get very confusing for someone that's focusing on implementing a native mobile application, right? So when trying to expose native library to JavaScript, you need to write this spec manually, and on top of it, you need to maintain the specification and the bridging. So if I want to bring like a SQLite library, I need to wrap it in a spec and create the bridging myself to call the correct functions. It's not directly exposed to JavaScript. This, as I mentioned, exposes you, the application developer, to learn all of this and maintain all of this to have access to some native third-party libraries. It can get quickly overwhelming. And we thought of how we can solve this. So our solution is to use WebAssembly, because it actually solves almost all of the issues I previously mentioned. Using WebAssembly bridges all the gaps we just talked about. And since the modules are sandboxed, there is no need to worry about triplets, platforms, and build systems, more or less. There is no issues with integration of different build systems. You can simply consume the WebAssembly binary, the pre-built, the artifact, and treat it like a library that just compiled and it's supposed to be linked with the application. And because the modules are sandboxed, we are also benefiting from its design of performance and security. So this allows us to use third-party packages, but with the grain of salt regarding the security, so we can sandbox and see effectively what is happening with this package.
Awesome. So now I'm going to share the results of my first journey into bringing WebAssembly for React Native. It started in October of last year. I wanted to build a proof of concept of wrapping specifically Wasmer in a native module for React Native to bring the API. And I started by building just a small TypeScript wrapper calling into this native module. So this basically implements the web part of the WebAssembly spec. And the native module underneath is implemented in C++, and it calls into the Wasmer C API. And it manually consumes this C API, so it's like manual code, and that's pretty tough to write, especially as a TypeScript developer. So this, I also built a small CLI that basically wraps the cargo CLI and builds Wasmer into this XE framework. So it's easier for consumption by the React Native tools. And I used the JavaScript core backend for Wasmer, trying to figure out like the different options for the different backends, and this was what I found most performant. And talking to Cyrus at the conference, the previous talk, it might not be the best thing for production apps because of limitations on the Apple platforms, and maybe it could be superseded by the V8 backend. So I haven't spent much more time looking into that. So a few words of caution. So it very limited subset that I did for this POC. So it's not implementing the entire thing. It's very limited. It only works on iOS. I don't claim to be an expert on Wasmer, and you shouldn't, like the benchmarks I'm going to show here, I might very well have missed opportunities to optimize. But this was like, I'm trying to tell the story of like what happened, and you should take it with a grain of salt. And if anyone is interested, I'd love to share the code. I want to build in public, but because it's such a rough stage, it won't be publicly accessible. I want to do it like a one-by-one basis. Okay? So with all those caveats and reservations out of the way, these are my initial results. The bottom line, it's a logarithmic scale, by the way. The bottom line here was the first thing that I tried. I'm computing Fibonacci numbers from a very small number, which is a trivial computation, to something that's, well, 5 is not that big of a computation, but it was basically around 300,000 and 360,000 ops per second, computing these load numbers. I wanted to figure out, like, this bridging that I implemented, how performant was it? And with some optimizations, I was able to get it to 1.8 million ops per second after I tuned. But like in the fairness of what actually happened, this is a result that I got later on. Okay, so the bottom line was what I was looking into, and I was comparing it to the same module running in Safari on the simulator, which was doing like 23 million ops per second. That's the upper line. So I'm like 2 orders of magnitude slower. And I was pretty discouraged by just looking into that. I was like, yeah. And then at that point was when I resurfaced and I was looking for alternatives, and I found that Callstack was actually building something leveraging ahead of time compilation. If I had spent a little more time doing these benchmarks, which I did later on, I learned that all of these lines are actually converging towards a pretty fast solution. That means when the workload is getting bigger, the computation I'm doing per call into the Wasm module, it's actually the same. And it's dominated by the bridging from JavaScript into So over this boundary, that's what's dominating these numbers. Yeah. My takeaways: Wasm is fast, and the overhead, I believe, is coming from this calling from JavaScript into Wasmer. And I believe ahead-of-time compilation and just-in-time compilation can be tuned with using specific Wasmer backends. And my takeaway is also it's not fun to maintain like one side of a C bridge as a developer. I think that's not a lot of fun, and it's partly also why I sunset the POC. Yeah, and again, Callstack was making a lot of progress with this thing called Polygen.
Yes. So we would like to talk about our new project we call Polygen. It's fresh off the oven. It's still very experimental, so we just want to share our use case of WebAssembly and how we are actually using it and what was the experience really. So let's talk about what is it. Polygen is our new approach to running WebAssembly in React Native. It's a highly performant solution that uses CodeGen. More on that in a few slides. It is compatible with Web API, which brings us closer to truly universal applications. It can be seen as the alternative to TurboModules I mentioned, and it simplifies embedding and consuming of third-party modules a lot. So we are actually more focused right now on using WebAssembly as a canonical ABI, but there's much more to it we are still about to explore. Let's talk about how it works. It compiles WebAssembly to C code rather than doing JIT compilation. This is because we are compiling WebAssembly to C using the wonderful Wasm to C tool from WebAssembly binary toolkit. To connect it with React Native, we also generate some additional code so it can be accessed from the JSI. Ahead-of-time compilation allows for near-native performance. It's very hard to reach truly native performance because of the abstraction here. And obviously, the resulting code is becoming the part of the application, just as you would link a static library or shared library. And we decide to use ahead-of-time compilation rather than embedding a runtime that uses JIT is because of the limitation on iOS, which is the biggest platform in React Native, is that the JIT is not allowed. So we are limited to either interpretation, which is slow, or doing ahead-of-time compilation to make it faster. So what it enables? It enables us to write truly universal applications using React Native and WebAssembly. Your applications will work both on React Native and the web. You can leverage existing, constantly growing WebAssembly ecosystem in React Native. Actually, one of those examples I first did was to use Rust's crypto library, because in React Native it's not provided. So it's actually possible right now to use Rust's crypto functions using Wasm bingen in React Native, which makes it completely easy to bring those external libraries. Finally, you can extend React Native functionality with languages other than C++. So writing polyglot business logic, and by the way, this is the name where the name comes from. It's the combination of the word polyglot and code generation, so it's called Polygen. Any language that compiles into WebAssembly can be used. Obviously, we get best of both worlds because we can use React for UI, which we see as the best fit, and everything else that compiles to WebAssembly to actually write your business logic. For example, you could use Rust or Go in the core and just our favorite stack, which is React and TypeScript, just for the native UI. So one of those use cases is, let's say you have a web app. You have native WebAssembly modules right now for performant computations, and you want to make a native application. Assuming the web app is written in React, it should be really straightforward. But because of the WebAssembly, it's not that easy right now. And Polygen allows you to do just that. You can easily make a native application out of your web app if it uses WebAssembly. And the other way around is that when you have a React Native application and you use native functionality, you were only left out with TurboModules. And this limited your options to create a web application out of it. So you need to maintain both WebAssembly of your native functions and TurboModules, which is suboptimal. And Polygen allows you just to do that. You can only use WebAssembly to embed any native external libraries. And a quick note about the initial benchmarks. So it's very early in the development, and we are still not that really focused on the performance, mostly as a canonical ABI to simplify the embedding and bringing the different libraries. So as you can see, we are still slower than Safari at the lower numbers of Fibonacci sequence, mostly to the overhead of the communications with JavaScript, and it's really hard to beat just-in-time compilations in some workloads. But as you can see, past, I think, 13 number in the sequence, we are gaining ahead over Safari, which is really nice. We're still aiming to compare it to truly native approaches, but that will be in the future after we manage to iron out all the current functionalities of WebAssembly. And there are still some possibilities to squeeze some performance with some flags and some smaller optimizations. Yes, so what's our future plans? We want to bring support for the remaining WebAssembly features, such as threading, single instruction, multiple data, GC, exceptions, all that. We'd love to explore adding support for more WebAssembly runtimes, like Wasmer, Wasm time, and any other. We are planning to do something like JSI, but just for WebAssembly runtimes. So you have a single interface, and you can use whichever runtime fits you the best. And one of the other feature plans we are looking at is leveraging WebAssembly components. So we call this WebAssembly mobile interface. And we would like to use widths and IDLs to expose native UI APIs to the so you can use polyglot approach. In this example, it's a quick example of like accessing the user's calendar so that it can be used from Go or Rust. Or as an alternative, you could use like a notification service. So you can send a push notification from your module, and it should be both doable on browser and on native site, which brings us closer to universal apps. And this is just a preview of how it could look like to write those, to consume those web APIs on native, not native applications. So yeah, it's pretty cool. We would love to see it working one day, but this is our goal right now. And just a quick recap about those web APIs. Those web APIs are already written in IDL, which WIT is based on. Here's an example of web IDL of crypto service. So it shouldn't be that hard to bring those to native computing, to the native languages. And we could derive width from those web IDLs with some annotations. So it should be really possible, we believe. And this is all from us. Thank you very much. And yeah, you can see the slides on our GitHub, and you can see our project on GitHub. It's under the Callstack incubator organization. And yeah, we just wanted to share our progress and how do we use WebAssembly, which is a bit different from the normal use case. Thank you very much.
Thank you.
Thank you.